Guys, so our topic for today's lecture is principal component analysis, and this is Dr. Dibya presenting you the lecture series on machine learning. Well, the main idea of principal component analysis is to reduce the dimensionality of a dataset consisting of many variables correlated with each other either heavily or lightly, while retaining the variation present in the dataset up to the maximum extent. So main thing you need to focus that PCA is what? PCA tries to reduce the dimensions of the dataset. Now, this is done by transforming the variables to a new set of variables, and they are known as our principal components or simply the PCs, and are orthogonal, ordered such that the retention of a variation present in the original variables will be decreased as we move down in the order. Okay, that's why we do this principal component analysis. Now, reducing the number of variables of a dataset naturally comes at the expense of accuracy, but the trick in the dimensionality reduction is to trade a little accuracy for simple means for simplicity. Okay, so you have to note down that while we are performing the dimensionality reduction, then this will come at the expense of some accuracy, means to trade a little accuracy for simplicity, because smaller data sets are easier to explore and visualize and make analyzing data much easier and faster for machine learning algorithms without extraneous variable to process. So we try to cut down that extraneous variables through this type of dimensionality reduction technique. Now, steps involved in principal component analysis. First step is the standardization step, and this is very important, and I have already explained what do you understand by the standardization through practical implementation in Python also. So let's discuss this step. So step 1 is for standardization, and the aim of this step is to standardize the range of the continuous initial variables so that each one of them contributes equally to the analysis. And once we did this standardization process, all the variables will be transformed to the same scale. You guys will see that when I put something in bold or in different color, this means this is very important for you, and thereby actually I indirectly asking you to note them down. Okay, then mathematically this standardization can be done by subtracting the mean and dividing the standard deviation for each value of each variable. So z is equal to value minus mean divided by standard deviation. That's the formula. Then step 2 is what? Covariance matrix computation. And the aim of the step is to understand how the variables of the input dataset are varying from the mean with respect to each other. And in other words, to see if there is any relationship between them. Okay, because sometimes variables are highly correlated in such a way that they contain some redundant information, and our motive is to reduce that redundant information. So, in order to identify these correlations, we will compute what? Covariance matrix. I hope you know what is covariance matrix. If you don't know, doesn't matter. I'm going to explain it to you. So the covariance matrix is a P cross P symmetric matrix where P is the number of dimension that has entries the covariances associated with all possible pairs of the initial variables. Suppose a three-dimensional dataset with three variables x, y, z. Then the covariance matrix is a 3 cross 3 matrix of the form covariance xx, covariance xy, covariance xz, covariance yx, covariance yy, covariance yz, then covariance zx, covariance zy, covariance zz. So what you'll notice that in the diagonal you have covariance x's, covariance yy, covariance zz. Okay. Since the covariance of a variable with itself is its variance, so covariance A is equal to variance of A. And in the main diagonal, top left to the bottom right, we actually have the variances of each initial variable. You will see that this is very simple because covariance x's, that is variances of x, similarly covariance yy, variances of y, covariance of zz, variance of z. And since the covariance is commutative, means you know covariance of AB is equal to covariance of BA, that is popularly known as commutative property. So the entries to the covariance matrix are symmetric with respect to the main diagonal, which means that the upper and the lower triangle portions are, equal. Note down this, very important, okay? Upper and lower triangle portions are equal. So, what do the covariances that we have as entries of the matrix tell us about the correlations between the variables? These questions obviously comes to our mind. So answer is it's actually the sign of the covariances that matter. If positive, the two variables increase or decrease together, means they are correlated. And if it is negative, one increases then other decreases, and that is also known as inversely correlated. Clear? Now, third step is compute the eigenvectors and eigenvalues of the covariance matrix to identify the principal components. You might recall from my assignment that I asked you to prepare some notes on eigenvectors, eigenvalues of linear algebra, because they need to be used in case of this type of ML preprocessing techniques or ML algorithms, or here in the dimensional reduction techniques. So principal components are new variables, that are constructed as linear combinations or mixers of the initial variables, and these combinations are done in such a way that the new variables are uncorrelated and most of the information within the initial variable is squeezed or compressed into the first components. So we have to find out the principal component based on calculating these eigenvectors. Okay. So if your data set is of 5 dimensions, then 5 principal components are computed such that the first principal component stores the maximum possible information and the second one stores the remaining maximum information, and so on. So you get the idea. Okay. So an eigenvector, giving you a brief idea, an eigenvector is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it, and the corresponding eigenvalue is the factor by which this eigenvector is scaled. You have to note down that for every eigenvectors, there is an eigenvalue, and the dimensions in the data determine the number of eigenvectors that you need to calculate. So let A be a square matrix, in our case the covariance matrix. So V be a vector and lambda is scalar that satisfied A V is equal to lambda V. And then this lambda is called eigenvalue associated with eigenvectors of A. So this is the formula. A V minus lambda V is equal to 0. A minus lambda I this stands for what? The identity matrix that V is equal to 0. And step, since we have already know that V is a non-zero vector, only way this equation can be equal to 0, that is determinant of A minus lambda I is equal to 0. So this process will be continued. I'll explain the remaining steps in the next lecture. So stay tuned to the next lecture. Bye bye.